Hello, and welcome to Quasar Does Astronomy. I'm your host Quasar, and today we will be looking at Kepler's laws of planetary motion. Kepler's laws of planetary motion describe the orbits of the planets around their home star. Kepler's laws laid some of the groundwork for Newton's law of universal gravitation, which we'll cover next week. Kepler's laws are as follows. Number 1. Planetary orbits are elliptical, with the Sun at one focus. Number 2. A planet will sweep out equal areas in equal time as it orbits around the Sun. And 3. The orbital periods scale with ellipse size, such that the period squared is proportional to the semi-major axis cubed. These laws build upon each other to describe how planets move through our solar system. Now, let's take a look at each one of those laws individually. Planetary orbits are elliptical with the Sun at one focus. This describes every planet in our solar system and every planet we've discovered outside of it. So let's go ahead and talk about orbits. All orbits can be described by conic sections. An ellipse is merely one type of conic section. A conic section can be thought of as different ways of slicing a cone. So let's go ahead and look at the different conic sections. Here you can see the 4 different kinds of conic sections: a circle, an ellipse, a parabola, and a hyperbola. There are 2 groups we can place these orbits in: bound and unbound. A bound orbit is an orbit that is bound to the object it is orbiting gravitationally, and an unbound orbit is an orbit that is not bound to the object it is orbiting. A circle and an ellipse are examples of bound orbits, and a parabola and hyperbola are unbound. A bound orbit would be an orbit like our moon around the Earth, or the Earth around our Sun. These objects will continue to orbit the central object until an outside force intervenes. On the other hand, an unbound orbit can be represented by something like a gravitational slingshot orbit, which basically means that a scientist has launched a satellite, and that satellite has come very close to a planet or other celestial body in our solar system, and it's used a hyperbolic orbit in order to move close to that planet and pick up speed. Then it leaves that planet and is no longer bound to it as it travels further through our solar system. Moving on to the second law, another way to describe it is with the equation L equals m times v times r equal to a constant. This equation states that the angular momentum, L, is equal to the mass m times velocity v times radius r, which will always remain constant. Let's take a look at an example. For this example, we'll assume that no mass is lost during the orbit. However, even if the overall mass changes, the concept still holds true. So what this example shows, and what this law means, is that as the distance from the center of mass decreases, the orbiting object will speed up. And as the distance increases, the object must slow down. So, in this example, areas A, and A, while they look different, all contain the same area. And even though T, T, and T all look like they have different distance lengths, are the same amount of time. So, finally we'll move on to the third law. This law is probably the most well-known, as it comes with a very famous equation you'll have seen if you ever take an astronomy course or a physics course. This equation describes the relationship between the semi-major axis and the period of an orbit. The equation is written g times m1 plus m2 over 4 pi squared times p squared is equal to a cubed, where g is the gravitational constant, m1 and m2 are the masses of the star and object, p is the orbital period, and a is the length of the semi-major axis. Now, the cool thing about this equation is if we use a measurement in years for p and a measurement in astronomical units for a, the equation reduces to p squared equals a cubed. Now, for those of you that don't know what AU means, AU is an abbreviation for astronomical unit. An astronomical unit is the approximate distance the Earth is from the Sun at any one point in time. Now, we can also rearrange that first equation to solve for the mass of one of the objects or for the total mass of the system. Now, if one mass is vastly larger than the other mass, we can assume that mass to be negligible and calculate the mass of the big object. In an example, Jupiter is much larger than the mass of any one of its moons, so we can use this example to calculate the approximate mass of Jupiter. Now, it is the mass of the total system of Jupiter and the Moon, for example, Jupiter and Ganymede, one of the Galilean moons of Jupiter. However, because Jupiter is so much more massive than Ganymede, we can take that assumption and approximate the mass of Jupiter. Now, one thing it is crucial to understand when you're talking about Kepler's laws is that at the time Kepler had written these laws, he did not know why these things happened. He merely used observations and trial and error to determine what was going on with the system of planets. We would not know why these celestial bodies behaved in this way until Newton came along with his theory of universal gravitation. Now, we'll cover that, like I said earlier in the video, in next week's video. So, you'll have to wait around for that one. So, that will wrap up my video this week on Kepler's laws. If you enjoyed it, please like and subscribe to the channel. If you have any questions or suggestions to make, please leave them down in the comments below. I'm Quasar, and this has been Quasar Does Astronomy. Thank you, and keep learning.